What's going on, Sam? Let's see. All right. We got we're just waiting on Jonathan. We'll jump in. All right.
Good morning.
Morning, brother. All right. All right. So today we're gonna do talk about conformational analysis. Thicker pen in there. And I sent videos on Friday for you to check out, just as a maybe as a refresher, but also just to get you kind of ready for what we're going to talk about. And so when we talk about conformational analysis, we're talking about the conformational analysis of a structure, like an alkene or even alkane or alkene. Uh, when we normally talk about this, we talk about the different conformations in terms of their energy. So we look at, right, the energy of a conformation, uh, and that's how we compare structures, right? So when you have an atom, when you have a molecule, let's say like butane, right, something like this, right? If we want to analyze that, we can look at butane here, right? Or we can look at the equilibrium structure, which is here with the two methyl groups on the same side, right? But a better way to look at that, and this one will be lower in energy because of those two methyl groups being opposite to one another. But there's a way to look at it and determine like what the energy is and to draw it differently. So the way we draw it is in what we call a Newman projection. So we're using Newman projection so we can see the interactions. Right, so we can see the interactions better if we draw Newman projection. So the way you do that is to pick two carbons in the chain and then use those two carbons as your reference points. Right, so one of them, the one behind, sorry about that. We'll take the one here. And then there's another carbon here, right? So one of those is going to be the front carbon, and one is going to be the back carbon. So if we want to draw this conformation where two CH3s are opposite, we're going to show that here in the Newman with a staggered conformation. And so the CH3 is now here, here, and here. So this is what you call a staggered conformation. And this is one of multiple conformations that you can have for butane, right? So, but this particular one is staggered, but it's also what we call anti, because it's the two methyl groups are the furthest apart. They're 180 degrees apart, right? If we want, there's another conformation, but before we do that, let's look here a little bit deeper, right? So the angle between the groups in a staggered conformation, the dihedral angle, 60 degrees. So that dihedral angle is 60 degrees in a staggered conformation, any staggered conformation. All right. And then the angle between the two methyl groups is 180. So that's why we call it anti. Let me fix that too. Right. So the dihedral angle is 60 between every group, the hydrogens, the methyls. And if we were to rotate one of the two carbons, we can do the back carbon or the front carbon, it doesn't matter. But we'll rotate the front carbon 60 degrees to close the angle down to 0. And then we can see another conformation, which would be what we call the Eclipse Conformation. So I'm going to keep the back carbon how it is. And we're going to rotate, we'll rotate counterclockwise. So this hydrogen, let me highlight them. This one, this hydrogen, and then the methyl, I'll make a different color. Right, so the green hydrogen should be here. Right, and now it's eclipsing with the methyl group that's up there. And then the methyl should be here. The methyl group is there, eclipsing with that hydrogen. And then my other hydrogen is here. All right, so this conformation is what we call eclipsed. And it costs energy for those methyls and hydrogens to overlap, right? So this is all here, here, all that steric strain. Right? The two hydrogens overlapping is more what we call torsional strain. It still costs energy for them to be overlapping though. I think for the eclipsed, this conformation, I want to say is uh, each methyl hydrogen overlap, I think it's 3.8 kilojoules per mole. And then there is, I think it's 1 kilojoule per mole for the hydrogen overlap. All right. Um, so that's going to cost you some energy. And so that's the whole purpose for being able to form different conformations is you have free rotation about that carbon-carbon bond, so you can get out of a bad conformation into a better one. Right. So we can take that eclipse conformation and we can move that front carbon back around 60 degrees.
Just where that cat stuff is over here.
All right. So if I move here, here, and here, that methyl group is going to come up here. You have a hydrogen here and a hydrogen here, and the back carbon stays the same. We're going to move that. Right. So this, where you have the two methyl groups 60 degrees to one another, we call this the gauche interaction. And it costs 3.8 kilojoules per mole for those two to be gauche to one another. All right. Um, so for butane, those are your well, we got one more where the two methyl groups will be eclipsing one another. All right. So what your methyl eclipsing interaction, I think that costs 11 kilojoules per mole. I said hydrogen was 1 kilojoule per mole, if I'm not mistaken. And then the methyl hydrogen overlap is 4 kilojoules per mole. So methyl is 11 kilojoules per mole. Right, that's a lot of energy. And so obviously the most stable conformation for butane is here in the anti-conformation. All right. So the way you get in and out of those different conformations is through bond rotation. You rotate around a carbon-carbon single bond. It's not free rotation because it costs some energy in order for you to rotate. But the energy kind of pans out at the end because you get to a better, more stable, lower energy conformation. All right. So as far as the acyclic um, structures go, you can always use a Fisher projection, a Newman projection, uh, to depict the conformations of a acyclic system. It doesn't matter how long the chain is. You always just pick two carbons in the chain and then use those two carbons to draw your uh, Newman projection. All right. So when you think about cyclic systems, right, which is where we're going with this, right? Normally for a cyclic system, you can have different ring sizes, three-membered rings, four-membered rings, and those 3 and 4 membered rings are pretty strange. So we have a cyclopropane, sorry, or cyclobutane, right? Those have ring strain because of the angles between the carbons, right? So if we did for the 3-membered system, if we did a Fisher projection like so, keep saying Fisher projection, Newman projection. right? So you have here, here, and then of course on the other carbon you have hydrogens as well. So the smaller the ring is, the more compressed these dihedral angles become, and that's where your ring strain comes from. So those dihedral angles get compressed. Right, so you got compressed dihedral angles. That's going to give you some more ring strain. It'll be the same for a 4-membered ring if we draw it in the form of a Newman projection. Same thing. Right, you're going to have some compression because of the size of the ring. If you look at and that dihedral angle, it widens as the ring gets bigger. So your most stable ring system is obviously going to be a 6-membered ring. Right, that bond angle and the dihedral angle is about as close as you can get to the normal geometry for carbon um, in a ring. Right, it's close to 109.5. All right, so you have uh, if we were to take the 6-member ring and draw it in the form of a Newman projection, we could draw it like this. Right, where now we got hydrogens here and here like that. And then that angle opens up to close to 60. And then be the same thing here. So the dihedral angle opens way up. And so that larger dihedral angle is gonna result in more stability for that 6-member ring. All right. So when you think about the 6-member ring and you think about the depiction of it, right? You normally don't see it depicted as a Newman projection. You see it predicted as a chair. Oh, there's a lag. It's coming up. All right, so you will see this depicted normally as a chair. Uh, and you can draw that like so. And if you watch that video that I sent, then it should be a good refresher. I'm not sure. The last several semesters, I haven't been able to get to chairs and boats in organic 1. So the chair can exist in a couple of different conformations, most of them higher in energy than your traditional chair, but you can have what's called a half chair. Oh, sorry about that. All right, this is what you call a half chair. And that's about 10.8 kilocalories higher in energy than the traditional chair. So 10.8 kilocalories per mole higher in energy. Right, then you can have in between that chair and a half chair, right? You can also have a bolt conformation, which looks like this, where both of those uh, ends of that cyclohexane ring are pointed in a axial direction. All right, so this will be considered a bolt, which is the least stable conformation for uh, the 6-member ring, right? And then you can also have a total ring flip, which is here, right? Where the ring undergoes what's called a flip, which is an example of conformational mobility in a 6-member ring. And again, the mobility part is important because you need to be able, or the ring needs to be able to get into more stable conformations from less stable conformations. So that's the whole purpose or the whole reasoning behind the ring flip. And I'm going to talk about that in a second, because if you have a substituted chair, right, we can, if we say it's mono substituted, right, with one substituent, that substituent is going to prefer to be in what you call the axial conformation. Hopefully you remember that. So you have on your chair, you got 6 different positions on there for each carbon. All right, so you, on each carbon, you have a position axial, which is vertical, and then equatorial, which is horizontal, right? Somewhat horizontal, right? And on every one of these carbons, you got the same exact situation. One axial spot, one equatorial spot. Same here. One axial, one equatorial. Same here. One axial, one equatorial. Right? So anytime you put a substituent on that ring, it's going to prefer to be equatorial. Right? If it's axial, I'm just going to put like a phantom substituent up here. Let's just say bromine. If I put a bromine here, let me move this down too. Right? The top face and the bottom face of the ring are both have, axial sites. So if you put a substituent on an axial site that's pointed vertically but downward, it's going to have the same impact, right? It's going to experience the same interactions. So on the chair, the axial hydrogens here are going to interact with that bromine. I think bromine is 1 kilojoule per mole to be axial. And we're going to talk about that later with the A value and all that stuff. But you have, if you got an axial substituent, it's going to interact with those other 2 axial hydrogens, right? So the whole idea behind doing a interconversion or a chair flip would be to alleviate that, right? So in a chair flip, everything that's axial goes equatorial and vice versa. So over here, the chair flip is going to look like this, where this carbon is going to be pushed down this way, and then this carbon over here is pushed up that way, right? So all of your substituents are going to kind of invert, right? So the bromine that was axial on this carbon, wrong pen. is not going to be equatorial. And then all your other hydrogens are going to swap too, right? But this is favored because those 1,3 diaxial interactions are now alleviated. Right, so the 1,3 diaxial interactions over here are alleviated when you do a chair flip. So that's why conformational mobility matters. Sometimes you can have a chair that's locked in a conformation, depending on like if it's in a bicyclic or a tricyclic system, like in a steroid or in a cholesterol molecule, you'll have um, your chairs are kind of locked and they can't interconvert. But as long as a chair is able to interconvert, then you can alleviate bad interactions. All right. Any questions about anything so far?
Not at the moment.
All right. So now there's a problem on that problem set that asks about this, and it says use a table of A values. So the A value or the Arrhenius value, right? That comes basically from the delta G of the equilibrium between two conformations, right? So for a methyl group, that's what I write. Being axial, if we took this molecule right here or this chair, where we had a methyl axial, and then this is an equilibrium. With the chair flip isomer where the methyl is axial. Right? So the difference in energy is going to come from the calculation where we look at the 1,3 diaxial interactions and calculate the energy of one isomer and then compare it to the other. So this is actually, it calls for the methyl to be axial, actually costs 3.8 kilojoules per mole. And we're going to talk about that. So it'd be 3.8 kilojoules per mole times 2 interactions. Right, because you got 2 axial hydrogens that are interacting with that methyl group. So it's really 7.6. So the total energy for that is 7.6 kilojoules per mole. Right? So the difference, and then with it being equatorial, right, the energy of this isomer would be 0, roughly. So your delta G for that would be 7.6 kilojoules per mole, or you can use kilocalories. You would just divide the kilojoules by 4.184. So let me do that real quick. Should come up to like 1 point something. 7.6. This is 1.81. So 7.6 kilojoules, 1.81 kilocalories. Right, so that number, that delta G number, we also call that the A value. Right, so the A value is how much the difference in energy between the two isomers. Right, so if you were to calculate the equilibrium constant, and this was at room temperature, the way you would calculate that is by using that Arrhenius equation, right? Delta G equals minus RT natural log of K, right? So you can solve for K, and it will be E to the minus delta G over RT equals K, right? So that's a way to do that. I can give you, I found a nice little article on this with a shortcut in it, so I'll give you that too, as far as how to calculate K. So the equilibrium constant will be 10 raised to the 3/4 delta G. So you can calculate it that way. And then if you want to calculate the actual rate constant, K, it will be 10 to the 13 minus 3/4 times the activation energy. Right, but we're going to focus on the equilibrium constant, K. So if we plug in the equilibrium constant, K, using the numbers that we have a delta G in kilojoules as well as in kilocalories. And the R, of course, the gas constant R is going to depend on whether you're using kilojoules or kilocalories as well, right? So you can calculate the equilibrium constant for any isomer. And if it's mono substituted or if it's di-substituted or tri-substituted, right? It's just a matter of knowing the values or the energy values for your substituents being axial, right? Because even if you have a di-substituted system like this, right? Even if you have a chair that's di-substituted, you're still going to have the same interactions. So let's say I put it a chair here, and I have a methyl group that's axial here, not there. Sorry about that. Methyl group here, and then I have another methyl group here, right? On that bottom face, you're going to have the same 1,3 diaxial interactions that you would see for the top face. Right, so instead of this just being 7.6, now your energy for this is going to be 15.2. Right, and then you can go in, you can convert that to kilocalories, and then calculate the delta G from that, right? Because the delta G is always going to be for something isomer like this where both groups are axial. When they both go equatorial, the energy is going to go down relatively to zero. That won't always be the case, because sometimes you can have an isomer that has one axial and one equatorial, like that. And then when you do the chair flip, you'll still have an axial substituent. So the delta G, the energy of that the second conformation won't be zero. It'll be something else. But you can still calculate delta G based on that. All right. So as far as cyclic systems are concerned, we know how we see how to calculate the equilibrium constant. We know how to calculate delta G. We can solve for the equilibrium constant. You just have to be given a temperature, right? R is constant. The gas constant is either going to be in kilojoules per mole Kelvin or joules per mole Kelvin, however you want to calculate it. So yeah, so let's look at some other types of ring systems. Right, if you have a cyclohexanone, which would look like this, you have a substituent at the 2 position, like an R group, right? The preferred conformation for that cyclohexanone would be here, right? Well, here's your where R is equatorial versus the equilibrium, which would look like this. The chair is terrible. Sorry about that. All right, this would be the chair flip isomer, but this is the preferred isomer here, where R is equatorial. All right, same thing. The 1,3 diaxial strain of R being axial is diminished when you make R equatorial. All right. If you have a similar system, but but your R group is something different than just a regular alkyl group, right? Then the dynamics change and the preferred isomer also changes. So if you put again, you have a cyclohexanone, it's going to affect the substituent in the sense that the substituent may prefer to be axial, may prefer to be equatorial. It just depends, right? So let's look at, let me show you how that works in terms of the energetics. If I have a substituted chair like so, fix that bond. And then if I had the same chair with a ketone, right? The A value for the methyl group on this chair, again, we already calculated that at 1.81. A here is actually, it drops to 1.3, right? If you think about it, you can see why. On this chair over here, you're going to get these two 1,3 diaxial interactions, one here and one here. On this chair, you have one 1,3 diaxial interaction, and the ketone is positioned away from the methyl group because of the geometry, right? It's 120 degrees, it's sp2, so it's going to be positioned away from that methyl group. So with that, you actually lose one of those 1,3 diaxial interactions in the case of a cyclohexanone like that. So then the energy drops because you lose one of those 1,3 diaxial interactions. Right? If you take the same cyclohexanone and you put a halogen in that alpha position right next door to the carbon that has the carbonyl, you see something different. You see something that we call the alpha halo ketone effect. Right? So if I take this chair and I got chlorine here, and this is in equilibrium with the chair flip, where now my carbonyl is here, and then the chlorine is now equatorial and not axial. Let me redraw that ring, because that it's hard to tell that that's equatorial. Right. So in this isomer, the first isomer, you can see it here that your dipoles are going to be opposite directions. They're going to cancel each other. All right. If you look at the other isomer, you can see that the dipoles actually are going in the same direction, even though it's kind of difficult to see it from the way it's drawn, but they're going in the same general direction. Right. So there's an additive effect for your dipoles. So it depends on, for these alpha halo ketones, these 6-member alpha halo ketones, your the stability is going to depend on the solvent, right? In a more polar solvent, you want your dipoles to align. So this is going to be more stable in polar solvents. And then for the other isomer, where the dipoles cancel, this conformation is going to be more stable in non-polar solvents or apolar solvents. Right. And so that alpha halo ketone effect is seen and it's understood based on the polarity. So this is more of an electronic effect. And you can see here that even with 2 1,3 diaxial interactions from the hydrogens that are on this ring here and here, the electronic effect outweighs the steric effect, right? For chlorine or for the alpha halogen. Right, because this is favored in a non-polar solvent. And we put it in a polar solvent, the equatorial chlorine is more favored, but it's counterintuitive, right? You would think that chlorine being axial in any case is going to be disfavored, but that's not always the case. When you put a halogen next to a polarized group like a ketone, then the electronics take over. The fact that those dipoles cancel each other out. Uh, that's the drop. That's kind of like the stabilizing factor here in a non-polar solvent. And then in a polar solvent, when the dipoles line up, that's the stabilizing factor. So it's not necessarily the sterics that controls this type of effect. It's the electronics. All right, we got a few minutes left. I'm gonna hold off on this anomeric effect until Wednesday. We'll talk about that Wednesday. Any questions with anything we talked about so far?
As long as it's posted, I'm good to go.
All right. All right.
I'm
I don't
good.
want to start the next topic, the anomeric effect, because I don't want to start it and then run out of time. So I'm gonna just hold off on that, and then we'll pick that up on Wednesday. We'll finish talking about these 6-membered rings, and then we'll also talk some about go back and review the A13 interaction and then an A12 interaction. We'll talk about that. So we'll stop here. We'll pick it up on Wednesday.
Okay.
All right. Thank you.
Thank you.
Have a good one.
All right. You too.